Hi, my name is Nathaniel Merson. Welcome to my AE1601 glider project. The name of my glider was the Dart, and we'll see why later on. The goals of this project were to first create a glider that can fly a minimum of 20 feet, and we also had to research pros and cons of different designs, and we had to use the provided balsa wood and or other housing materials to build the glider. We had to make a couple design iterations, and then also participate in the flight tournament with the class. The requirements first for design were that we had to make an initial design, then make at least one design iteration, and the success measure for this was that we had the checkpoints in this presentation. For the construction, we had to make a final glider that fits inside a 16-inch by 16-inch square, and it was also made with the appropriate materials, which was most of the provided balsa wood. It must also be a glider, which means that it has wings and does not have self-contained propulsion. And the success measure here was that we had the correct material choice and size. For the flight, the glider must be hand thrown in the competition, and it must remain intact after the competition throw, and must go at least 20 feet. The success measure here was that it was intact with a good distance on the competition throw. Looking at the different wings I could use, first I'm going to take a look at the straight wings. They were the easiest to manufacture and also have the most wing area, but they also have some of the greatest drag. For the taper wings, they're more efficient than the straight wing, but they're also harder to precisely manufacture. The delta wings are harder to break because of their shorter wingspan, but this also means that they have a lower aspect ratio, which is better for gliders. But the lower aspect ratio also means that you can throw it harder because it's also going to be more difficult to break on impact. But this also comes with a side effect of relatively high drag. The elliptical wings are very efficient, but they're the most difficult to manufacture and analyze. The swept-back wings have a large aspect ratio, but they're inefficient at the speeds that we're going to be looking at. For the design process, there's also a couple of different materials that we could use. Cardboard is easy to build with, and as there's no concern of running out of materials, you can build stuff with it fast, and it's easy to cut. But it lacks structural integrity, and it gets floppy after a few tests. But at the same time, it's also decently heavy, which means that we're losing valuable efficiency. The balsa wood is lightweight, and it's also stronger than cardboard, which means that there's less risk of it breaking and weakening, but it's also a scarce resource, so we have to be careful of the amount available. I could also take a look at 3D printing different parts, which would mean that the parts would be completely custom and allows for different designs, i.e. dihedral wings, but that also comes with a large construction time, which is be inefficient for this project. Taking a look at the different adhesives that I could use, first is hot glue, which is easy to apply and easy to iterate and test with because of its quick hardening times, but it's also heavy and bulky, which means that it could have aerodynamic effects. Super glue has fast hardening times, it's also strong and lightweight with no aerodynamic hit, and the same thing goes for the CA adhesive. For epoxy, it's difficult to obtain, but it fills the gaps, so it's going to very well attach to different parts, but it has long curing times, which means that it's unrealistic for quick testing. So what should I use? Which has the high success probability? For the wing shape, in my first two designs, I used taper wings, but I failed to see results, so I moved on to trying delta. This is what I ended up using for my final design. For the material, I ended up using my Cobra for all my testing because it was easy to test with, but for my final design, I had to use the balsa wood because it was the strongest and also something that we had to do. For the adhesive, for all my testing, I used hot glue because it was easiest to put the pieces together and also want to be semi-removable if I wanted to remove the wings and put something else on. For the final glider, though, I used CA adhesive because I knew that it would have the least compromise for my final build. Sizing through the iterations first, in my first design with the taper wings, I ended up with an aspect ratio of 14.1, which is very high. But in my final design, as I moved on towards a delta wing design, I ended up with the aspect ratio of 6.67, and you can see all the different measurements there. So why did I pick what I did for my initial concept? Well, I thought that taper wings are more efficient than straight wings because they have a high aspect ratio that's better for gliders. And I also realized that with that, I also had a center of gravity underneath the wing with the position that I had it at. And it was very near the core-to-core position. And I was going to get it exactly at the core-to-core position later on. I implemented horizontal and vertical stabilizers because I wanted to increase longitudinal and roll stability. And I also had the wingspan as long as possible because it leads to higher aspect ratio. I recognize the area for improvement in the wing area and wing support, but I did see good performance in general stability. Let's look at my test flight. We're going to see here that it flies very straight with no rolling. That indicates that it has high roll stability, high yaw stability, and neutral static stability because it went in the direction that it was thrown. And looking at the different requirements, it met everything except the materials check. So I saw the improvements that could be made. I needed to keep the center of gravity at the core-to-core length. I had to increase the distance thrown and switch from taper wings to delta wings because I thought that I could be able to throw it harder. I wanted to maintain the stabilizer size to wing ratio, however. So these are the 4 different planes that I ended up making. And we're going to take a look at the best test flights for each of these. So for the swept back design, it goes decently far. And then I moved on to the delta wing. That glides very well. As we're going, this is the final design that I ended up making. Let's look at this test flight.
One.
Okay, so we can see that it goes very, very far. and it has high general stability with no standard deviation from course and high longitudinal stability. It meets all the requirements, but I realized that the improvements I made were that I moved on to a delta wing design with a horizontal stabilizer tapered and a vertical stabilizer that was swept back. I added a mass component of 20 grams to the nose, so the overall weight was 35 grams, and the collision of center of gravity was 2.5 inches from the front of the glider. Looking at my different coefficients of lift and drag, I ended up with a coefficient of lift of 0.171 and a coefficient of drag of 0.003. So I need to recognize how iteration improved my performance. Going through the 4 different prototypes, I realized that design iterations allowed discovery the highest performance elements. These are the delta wings, the tapered horizontal stabilizer, the mass component placement, and the mass component amount. I saw the large tapered horizontal stabilizer, and it greatly improved the roll stability in the final model, and also realized the longitudinal stability improved with vertical and stabilizer modification. Performance over time went from 25 feet with the initial design up to over 110 feet in the final performance, and I even ran out of range markers on competition day. Look at my best flight on competition day. You can see that indeed goes very far. My flight distance was over 110 feet, and it met all of the appropriate requirements, including the size. You can see it aligned with a 16-inch wide size right there. Looking at my summary, all the original goals were met. I researched, developed, and constructed a balsa glider that was within the size constraint that flew a minimum distance of 20 feet. But I also realized that researching is only one path of success. Prototyping and iteration is the other half. I realized that I can improve the design by making wings a higher aspect ratio, and in this instance use a delta wing design with a much wider wingspan. This would mean making a wider triangle base. I could also decrease the size of the vertical stabilizer because the glider is already stable enough, therefore it's adding more drag. I could increase the horizontal stabilizer size because more roll stabilization is always worth it, and it adds potentially more lift. But I also have the implementation of integrated wings, aka not on top of the fuselage, rather through it, which means that there would be less added drag. These are my sources. Thank you.